Talk about some properties. And here's how we're going to get the properties. We're going to use everybody's favorite coordinate system, Riemann normal coordinates. So the very first thing we're going to do is lower the index. So of course you know how to lower indices, but for effect, let's write the equation. We're going to actually talk about it in the lowered index form. We're going to write out a bunch of stuff to help us see some properties. So we're going to go to Riemann normal coordinates. So those are the ones where g mu nu at a point P is equal to eta mu nu, and coordinate derivatives del alpha g mu nu at that point P are 0, which is the same thing as saying the Christoffel symbols at P are 0. And so in these Riemann normal coordinates, we have a somewhat simplified form of the Riemann tensor. So the Christoffel symbol terms will vanish at the point P, but we do have to worry about the derivative of the Christoffel symbols. So Riemann rho sigma mu nu at P in Riemann normal coordinates. If I felt like writing 100 little hats, I would put a hat over every coordinate index here to remind you this is in our special coordinate system near a point P. But this is going to be our metric, which we use to lower the index, times the formula for the Riemann tensor. But we're not going to need the terms that involve Christoffel squared. We're just going to need the derivative of Christoffel terms, because the Christoffel squared terms are all going to vanish because the Christoffel symbols vanish at that point. So we're just going to need the term derivative nu sigma minus mu goes to nu, del nu lambda mu sigma. The gamma terms go to 0 at P. And now we expand out the Christoffel symbols. So g rho lambda, I could change this to eta rho lambda at this point, but let me leave it for now. So there's going to be two terms, del mu of, and now we need a 1/2 g upper lambda nu. This is all, so that's an alpha, and then this is an alpha, del nu g sigma alpha. And then we have to add the other term, del sigma, right, this one, g nu alpha, and then we need to subtract del alpha g nu sigma. Okay, that's one term, and then we have the other one. And now we can see the g's here, this one, and this one are contracted with each other. So the inverse metric contracted with the metric is just a Kronecker. So that's going to be a Kronecker rho alpha times all this stuff. Maybe I won't copy it. I'll just write del mu of all that stuff minus del nu of all that stuff. So that's just going to set nu equals to alpha. So now I will write it out. There'll be a 1/2. I guess I can pull the 1/2 out here. So there'll be a 1/2 times all this stuff. Now you have to, I was allowed to move the inverse metric through the partial derivative because this is going to be at the point P. I should be writing that down explicitly at every time. And so the first derivatives of the metric will vanish, and so do they'll just vanish because g is equal to eta, but then there's no linear correction because its derivatives vanish. So I can move those out when I'm evaluating at a point P. And then I will just get a bunch of second derivatives in here. So I'll get del mu, del nu, g sigma alpha, plus del mu del sigma g nu alpha minus del mu del alpha g nu sigma minus del nu del mu g sigma alpha minus, so now I'm working on the bottom line, del nu del sigma g mu alpha minus del nu del alpha g mu sigma.
Shouldn't all the alphas be rho symmetric?
They sure should. Excellent. Hopefully that's it for the corrections. And then we should see some cancellations. Here's one. And so now we have this nice formula that R rho sigma mu nu at this point P in Riemann normal coordinates is equal to 1/2 del mu del sigma g nu sigma minus del mu del rho g nu sigma minus del nu del sigma g mu rho plus del nu del rho g mu sigma, again all at a point P. And this is very much in this special coordinate system. Now, like I said, you're not really going to construct this coordinate system in practice, but it's very useful for theoretical arguments such as this one. And what we're going to do with this at the start of the next class is we're going to realize that although this specific equation only holds in one coordinate system, certain properties of it, such as index swapping symmetries, are going to hold in any coordinate system. So as a preview, we already know it's antisymmetric on the last two indices. That came out of the definition. It's just sitting there since we defined it as commutation of covariant derivatives, that mu and nu were the indices. But we're going to see it's symmetric on the first two indices. Rho sigma, just from this form. You see this has sigma rho, but this is the same thing with rho and sigma interchanged in a minus sign. So the first two terms are antisymmetric on rho and sigma, and so are the last two terms, del rho sigma and sigma rho, right? So we see that Riemann rho sigma mu nu equals minus Riemann sigma rho mu nu. And this is a good tensor equation. Okay, so even though we derived it in special coordinates, it'll hold in any coordinates at any point P. And so this Riemann normal coordinate argument gives us a property of the Riemann tensor as a tensor. And we'll go through that next time and derive the rest of the properties that we need as well. Well, so we know from the last two, let me write that as well. So let's write the last two here. Rho sigma mu nu at P is minus R rho sigma nu mu at P. So we knew this already. But from the second one, where you do the same game, and you notice that swapping rho and sigma on the right picks up a minus sign, we get a new equation. And this equation starts out, we derived it in Riemann normal coordinates at a point P, but now it's just a tensor equation at the point P, right? There's no partial derivative of metric left, for example. Partial derivative of metric doesn't transform like a tensor. This thing circled is not a tensor equation, but now that we look at this particular implication of the circled thing, that is a tensor equation. And so we just know that this holds as a tensor. So the tensor R, rho sigma mu nu is antisymmetric on both pairs, right? So you can swap the first two indices and you can swap the last two indices. So that's a property of the Riemann tensor that you're going to need to use when you do calculations with it. I think it's nice to ceremoniously write them out in a list, so let me quickly copy this down. So let me show you another one, which I'm not going to write out, but you can see how it goes. It's the same as the other two. Maybe if you're really good at keeping track of indices, you can even eyeball it. The claim is that if you do cyclic permutations on the last three indices, they will add up to 0. So R rho sigma mu nu plus R, and then we keep rho the same, but we do cyclic permutation, so let's move them all over one. Nu sigma mu plus R rho, and the last cyclic permutation, we move them over again. Mu comes to the front, mu nu sigma equals 0. So in words, this is cyclic permutations on the last three indices. It's the same argument. You just write all these terms out and do the three cyclic permutations, and you'll find that all the partial derivatives cancel. So again, the argument is that the circled equation, well, that only holds in one coordinate system, Riemann normal coordinates. But when you do this funny business of adding it to itself 3 times, you get a tensor equation. And so you know you've derived a good property of the Riemann tensor that just holds at every point P. Yep?
So, kind of a notation question.
Mm-hmm.
Up above, we were evaluating at point P.
Yeah.
Since we're generalizing it to just be valid at any in any coordinate system, not Riemann normal coordinates, and we didn't really put any constraints on point P.
Yeah.
Is that why we're dropping?
Yeah, it's implicit. Yeah, it holds at any point P.
Okay.
We don't have to make a separate. It's nice to write the point P in the Riemann normal coordinates expressions, because there we have to make a separate Riemann normal coordinate system for every point P. In the properties 1, 2, and 3 that we've written down, it's just fix any coordinate system and go to any point. So we don't write the P. It turns out these 3 together imply another property, which we'll call property 4, but it's not independent. And this is the last annoying tensor manipulation I'll give you on the homework. You can show that these 3 make it clear that you're allowed to swap the 2 index pairs. So rho sigma mu nu is equal to mu nu rho sigma. Okay, so I've swapped, and it's not a minus sign, it's a plus sign. Swap the 2 index pairs. So when you guys attempt this on the homework, some of you will be very good at it and see right away what you need to do, and some of you will be like me when I remember doing this in grad school, spending hours just like randomly using these properties and trying to derive number 4. But I can't teach GR and not give you this problem, given my suffering. And it makes you, you know, actually internalize these properties. That's the real reason to do it. Okay. So another consequence of these that I won't go through is the number of independent components, right? So you'd have d to the 4 independent components in a rank 4 tensor, okay? But because you have these different properties, it turns out the answer is 1/12 d squared minus 1 independent components in d dimensions. So that's down from d to the 4, but still a lot. And if I remember right, that's going to give you 20 in 4 dimensions. Does that look right? 16 times 15 over 12. Is that 20? Good. Okay, so I do believe Sean writes out a paragraph deriving this, or you can do it yourself if you like combinatorics. And in 4 dimensions, then, there's 20 components. That's how many numbers it takes to specify the curvature of a 4-dimensional space-time. Okay, then another property that is useful is called the Bianchi identity. So first let me write it, and then we'll derive it. So the Bianchi identity, if I remember right, is cyclic permutations on the first 3 indices when you take a derivative. So del lambda r rho sigma mu nu. So I've just taken a covariant derivative of the Riemann tensor. And now I do the cyclic permutations game on the first 3. So del rho r, whoops, that's not the way I wrote it before. Let's be consistent. I moved them to the right. So it's going to be del sigma r lambda rho, and then mu nu just goes on for the ride. Del, I move them again to the right, rho r sigma lambda mu nu equals 0. So this is an algebraic identity. It's not a property of some physics or something. It's just any Riemann tensor you write down by the definition we gave will satisfy this. So let's see why. Same thing. The proof is, again, we go at our special coordinate system, Riemann normal coordinates. We realize that in the Riemann normal coordinate system, del lambda rho sigma mu nu could be written out as partial lambda r rho sigma mu nu plus a bunch of terms involving Christoffel symbols times Riemann. But fortunately, the magic of Riemann normal coordinates, right, if we evaluate this at a point P, what happens? Well, the Christoffel symbols by construction vanish at P. So we again get to just work with partial derivatives. So we can then just write that this thing is equal to that giant formula above, which is not on the screen, so I'll just copy from my notes. I just take a partial derivative of it. So I now have partial lambda, partial mu, partial sigma, g nu rho minus partial lambda of partial mu, partial rho, g nu sigma minus partial lambda, partial nu, partial sigma, g mu rho plus partial lambda, partial nu, partial rho, g mu sigma at P, since it's in our special coordinate system. And then it's the same game. You just look at the cyclic permutations of the first three indices, lambda, mu, rho, and I'm not good enough to see it in my head, but you get to use that we now have partial derivatives, so they perfectly well commute. Okay, so any of these first three indices in any of these terms can be interchanged, and you'll see that if you take cyclic permutations on the first three, then you get 0. And then you do the same argument. Well, you say, now I've proved that cyclic permutations with partial derivatives in the Riemann tensor I evaluated at a point P go to 0. And so you just promote that to covariant derivatives and say, OK, that's a good tensor equation, so the covariant derivative form must hold. Does that make sense, or should I write it out? Any requests to write all that out? Maybe just a couple words. So first of all, this is cyclic perm on the first three indices. And then so you derive the covariant derivative form, the coordinate derivative form, and promote to covariant R. They're equal at the point P, right, in Riemann normal coordinate, and then you've got it because you have a tensor equation. So that's our Bianchi identity, which is more exciting than you think. Okay, there's a sea of indices here, but this differential identity is actually going to end up, when we finally derive Einstein's equation, this differential identity is going to end up enforcing conservation of energy. Well, energy is not conserved in the universe at large. Like dark energy is a counterexample. It's a fixed energy density, and space is expanding. But locally, it is conserved. And the nice thing about gravity is it forces that. If you want your theory you're inventing to couple consistently to Einstein gravity, it has to obey local conservation of energy. And the Bianchi identity is part of that story. So some useful definitions for gravity. which is coming fairly soon, I promise, what we can do is contract our Riemann tensor. So remember, we had 4 indices. We could raise one and contract. The traditional one is the first one, since after all, it started out raised, right, when we defined it. Now, which index could we contract the first one with? Well, we couldn't do this. We can't do this because remember, the Riemann tensor was antisymmetric on the first 2 indices, right? So that would just be 0. I mean, you could do it, but it's not going to be a useful definition. It's just 0. And the one we choose is the third one. So we're going to write it this way. We could choose the fourth, but that's not independent, right? Because it's antisymmetric on the last 2. So at this point, it's just a choice. But we have this contraction. This is the only interesting contraction. And that's going to be called our mu nu, which is the Ricci tensor. So that is now a rank 2 tensor. It has some information about curvature, but not all of the information because we've contracted over a pair of indices. And because of property 4, that you can interchange pairs of indices, this is actually symmetric. So r mu nu equals r nu mu. Symmetric tensor. And it's a very nice tensor for gravity because it has 2 indices and it's symmetric. It feels like something that could, say, be set equal to the stress energy tensor, which had 2 indices and was symmetric if you wanted to make a field equation. You know, it's this thing, this Ricci tensor. It's been boiled down to a small notation here, r mu nu, but it involves within it a number of derivatives of the metric. In fact, 2 derivatives and 1 derivative and 0 derivative terms if you wrote this all out. So it looks an awful lot like a second-order equation on the metric, which is kind of what we're looking for to generalize Newton's equation. Yeah?
This is a two-dimensional. This now has 2 indices. It has 16 components. Where did the other 4 independent components of the
Well, it's symmetric, so it has 10. But what's the question?
I guess where do the other components go? I guess that are independent. Like, do they just cancel, or are they just in the terms?
What do you mean, go?
Well, we talked about how there were in 4 dimensions. There's
20.
independents for the Riemann tensor.
Yeah, well, I summed over a bunch of them, right? So I basically got fewer by taking particular linear combinations of the 20. That's all.
So they're in the components. There's a lot of them that are summed over.
Well, you don't, if I just gave you the Ricci tensor, you don't know what Riemann tensor it came from. You've lost information. But if you start with Riemann, you can certainly get Ricci. Yeah?
Like, how do you know that it's symmetric? Because like the Riemann tensor is only symmetric, antisymmetric on the first 2 and the last 2.
Well, no, there's property 4 that we can interchange pairs of indices. So if we lower it, let's do it. So if we write this as G lambda sigma r sigma mu lambda nu, then by property 4 it can be G lambda sigma r lambda nu sigma mu, right? Interchange pairs. And then that is the same thing as, well, that's just the definition of raising the index, Riemann sigma nu sigma mu, which is then the same thing as r nu mu. That's the proof. Okay? Other questions? Another thing we can do is contract one more time. So there's a definition. Here's another one. We define R without any indices, and this is a common notation for the contracted version of the tensor, as you just raise one index of the Ricci tensor and some. And this has a good name. It's the Ricci scalar. Now, if we thought we were just looking for a scalar equation because we thought Newtonian gravity, we're going to have Newtonian gravity, you have a scalar potential, it's sourced by the mass, then we might think about the Ricci scalar, which is a second order derivative operator acting on the metric, being sourced by the mass, but that wouldn't be very relativistically invariant because, energy is different in different frames, so Ricci tensor is a better candidate. But there's going to be an even better candidate, and we're going to get that by thinking about our Bianchi identity. So, to motivate a final definition, the Einstein tensor, see we're approaching gravity, G mu nu, consider the twice contracted Bianchi identity. So what do I mean by twice contracted? Well, let's write out the Bianchi identity. That was our cyclic permutations on the first three indices of the Riemann tensor. So that was equal to 0. That's the Bianchi identity, and now we're going to contract it twice. So G nu sigma and G mu lambda. So what I've done is raised, if you like, the nu, that index here, but raised it to be a sigma, so I'm contracting over nu and sigma. All right? And you can see that's a non-trivial contraction, right? That's the second and the fourth on this term. It would be trivial if I contracted over, first and second, because those are antisymmetric. Okay. So this is an interesting one to look at. Some of these terms might be trivial. No, looks like they're not, so they're all non-trivial. So this is 0. Again, algebraically, you take any metric, you make up 10 functions of 10 coordinates you're using for your manifold, and you write out that crazy expression, Riemann tensor, with all those derivatives of the metric and nonlinear contractions and all that, and you find the covariant derivatives, and you work really hard and you do that, and then you'll find that this particular combination of them is always 0. So what can we do here? So notice that this term is equal to minus del rho r sigma lambda nu mu. So I'm swapping the last two here, getting a minus sign. That was one of the properties we talked about. And then this term here, I am writing as plus del sigma r rho lambda nu mu. So I've contracted swapped both the first and second and the third and the fourth, so I get a plus sign. So let's see what we have here. So what's this first term? Remember, covariant derivatives commute with metrics. That's the whole point. We made the vanishing of the covariant derivative on the metric an axiom for finding the right derivative. So we can move these g's inside. And then we just have contractions. So this becomes del lambda r, so nu sigma, so rho. Maybe it'll be clearer if I swap this one too. Let's do that. So let's write this as plus del lambda r sigma rho nu mu. Again, swapping those two index pairs, so it's a plus sign. And now it's a little clearer that what we have here. Okay, so now it's just more simple. G mu lambda here, raise the index on the derivative operator. Done. Yeah. Okay, very good. And so I did that because now this thing is exactly the Ricci tensor we defined. It's contracted on the first and the third index, right? So that's going to become the Ricci tensor. Ooh, now what do we have here? And then I've got r, and I've got sigma lambda. So let's raise the sigma. That becomes nu. Let's leave the lambda. No, let's raise the lambda as well. That becomes a mu. Nu mu. Right? Good. And then what's our last term? Same story. The sigma, let's raise that to become nu. And then it's r rho Maybe I'll do it this way, nu mu. I'm a little confused why I would want to swap these, but anyway, I think I did this right. So this term is in the exact form of the Ricci tensor. So this is del upper mu r lower rho mu. This term is, well, this is the fully contracted, right? We've contracted on both pairs, so that's just the Ricci scalar, del rho r. And the last term, okay, I ended up on the second and fourth index. I could have been a little slicker if I had swapped these pairs or maybe left it in the original form. But anyway, if you lower and raise and so forth, this is just, again, the Ricci tensor. So that's del nu r rho nu. Okay. And so now we have an equation that took our Bianchi identity with the Riemann tensor with all four indices and moved it over to the Ricci tensor and the Ricci scalar. So this is all, of course, equal to 0. These two terms are the same. We can just relabel, it's a symmetric tensor. Well, they're contracted on the second index anyway. So these two terms are the same. So this tells us that del mu r rho mu is actually equal to 1/2 del rho r. Thank you. Even I saw that one. And so we can repackage this. We can define g mu nu is r mu nu minus 1/2 r g mu nu. And then it follows that del mu g mu nu equals del mu r mu nu minus 1/2 del mu r. The del mu doesn't hit the g mu nu because it's metric compatible, otherwise known as del mu r mu nu minus 1/2 del nu r, which is 0 by this equation. So this is star, then this by the star equation. Okay, so this Einstein tensor is a really good candidate for setting equal to the stress energy tensor because not only is it symmetric, it's automatically conserved, right? We've just proved that del mu g mu nu equals 0. Automatically, as an identity. So for any metric, doesn't have to satisfy equations or anything. So it's a symmetric divergence-free tensor, which makes it an excellent candidate for setting equal to the stress-energy tensor. If you tried to use the Ricci tensor, which Einstein did try for a while, then you end up with strange inconsistencies because the matter you do know about has a conserved stress-energy tensor, and if you set that equal to the Ricci tensor, which doesn't have to be conserved, you can derive some unphysical restrictions on the kind of matter allowed, which we'll go through when we write down Einstein's equation. Yes?
And the reason that we want this first derivative to vanish is just because we want it to match up with the stress energy tensor?
Yeah. Yeah, we're just, I'm imagining how Einstein approached this, and there's some evidence he did, He's looking for a generalization of Newton's gravitation equation, which is the Laplacian of phi equals the mass density. So the idea is, well, the relativistically invariant generalization of mass density is stress energy tensor. So we need some second order derivative operator acting on the metric that could be set equal to the stress energy tensor. So it ought to have the properties of a stress energy tensor, like symmetric and divergence free. That's divergence free is the conservation. And so we've now found a symmetric, write that in words, g mu nu is a rank 2 symmetric divergence-free tensor, just like t mu nu. So that's what's going to make it, in fact, proportional to t mu nu. That's going to be Einstein's field equation. Yes, Kush?
So that repackaged thing, right? We just
This means definition, yeah.
With that,
We wanted to find a symmetric rank 2 divergence-free tensor. And so we got our, that was second derivatives in the metric. So we found our Riemann tensor. That was our invariant thing that has second derivatives in the metric. And we said, okay, we got too many indices. We just want 2. So we contracted on 2 of the indices of the Riemann tensor to get the Ricci tensor. And then we said, okay, we want it to be conserved, so let's figure out what the Bianchi identity tells us. So we got this equation with a red star. And then we realized, aha, if we just define this new combination of Riemann and Ricci, then it will actually be conserved automatically as an identity. There's actually one other rank 2 symmetric divergence-free tensor. We've already met it. It doesn't have to be divergence-free. Yeah, the metric itself is another example. It's symmetric, right? It's rank 2. It's more than divergence-free. It has no derivative at all. We constructed the derivative so that the metric didn't have a derivative.
so we can solve the equation that you need the others. And get the circle inside.
Yeah, so I mean, this is when Einstein was thinking about, writing down field equations. I think he knew this, and that's the cosmological constant term. You could add a term that's proportional to the metric itself. We'll talk more about that. But this is certainly more natural from the perspective of Newtonian gravity, because the metric itself isn't derivatives of the metric, right? Newton's law of gravitation has derivatives of the potential phi. So Einstein didn't like the cosmological constant, and for good reason. But it exists in our universe.
Naturally popped up from that dimension.
Yeah, I don't agree with that. I don't think it pops out from anything. I think nobody expected it to be there, and it was only there when the astronomers carefully calibrated supernova light curves and convinced everybody it was there. It's not there in QFT, and you can make your own decisions studying the theory yourself. But if you just look historically, before the data, everybody thought it wasn't there. Nobody said there's really a vacuum energy. Okay, one point I should make about curvature, which has come up a few times, but I never emphatically made in class, is the difference between intrinsic and extrinsic curvature. So we've had a few problems, notably the cone one, that are basically exploring this difference without using those words. So you guys did a great job on the cone problem. This is the first year I actually asked people to make cones instead of describe how you make them. And if you found it was annoying, I'm sorry, but I feel like the results were so much better. like you all, pretty much everyone got the problem or got extremely close, and everyone made the right cone. So I was very happy with that combination of first grade homework and graduate GR homework. But the key point about the cone is when you made it, there was some cutting, right? You had to cut a wedge out. But there was no stretching. You didn't have to try to force the paper to stretch, right? You just took a portion of the plane and you connected it to itself in a different way. But you still had a portion of the plane. So that cone is still intrinsically flat, right? And you also proved that algebraically, because you found that the metric of the cone, even though it looked complicated originally, was actually just d alpha squared plus d beta squared, right? You put it in that form. So you actually proved that the cone as an embedded manifold, which we started with, is actually perfectly flat, right? In the sense that the metric is Minkowski. And we asserted last time that if the metric can be put in flat, in Euclidean or Minkowski form, it's equivalent to the Riemann tensor vanishing. So the Riemann tensor and these derived objects characterize intrinsic curvature, irrespective of how it's embedded. The cylinder is an even a better example because it really looks curved. If you ask a person on the street, is the cylinder curved? Of course, they'll say yes, and it is curved through the three-dimensional space, right? It looks like a circle. Everyone would call that curved. But as an intrinsic manifold, you didn't have to stretch the paper to make the cylinder, so we'd say it's flat. And the metric of the cylinder is, again, just the Euclidean metric, except you now glue this to this, right? Okay. By contrast, the sphere is curved. And I don't think I've had you calculate the Riemann tensor. I haven't, but you could. It's not so bad. That would be one way of seeing it's curved. You could try to prove that there is no coordinate system where it's Minkowski. I'm sure that's possible. That would be a more annoying way, or Euclidean, I should say. You could try to prove there's no coordinate system where the sphere metric is globally Euclidean. That would be a more annoying way to do it, but you could show it that way. And the physical way is, try making a sphere out of a piece of paper. You're going to have crinkles. You have to really stretch the paper, right? Or go get a globe or a little ball and try to put your paper around it without stretching it. It'll stretch, right? Yeah, or compute, right, the Riemann tensor. Okay, yes?
So is any example you can create by identifying just one plane flat?
Yeah. Yeah, because the plane metric is flat, right? Flatness is a local statement. The Riemann tensor is defined at a point. And it doesn't care about any finite region. It talks about derivatives, but it's still local in that sense. So if you start with a flat metric and add identifications, it's the same metric. It's just the coordinate ranges. And another reason I like to emphasize the cone problem is when you write down the metric, we always write ds squared equals blah, 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 blah. We don't always write the ranges of the coordinates. We leave that implicit, right? And this is especially evident when they are spherical coordinates, because the ranges are kind of weird, right? This coordinate r is only positive, and this coordinate theta goes from 0 to pi, except it doesn't really cover 0 or pi, and this coordinate phi is 0 to 2 pi, except you have to periodically identify. Like, we leave all that information off because you know it already, but it's part of the metric, part of the manifold. So when you give the metric on the manifold, you give the line element, and you give the ranges of